I want to say welcome to everybody. There's still a bunch of people that are joining in as we go, but we're going to go ahead just to save the time for the rest of you. This talk today is sponsored by ProEngine, and so that will be Scott. But I want to talk today about some emerging threats and the reason that we have to be focused on aerosols right now. So my name is Christina Baxter, and I own a company called Emergency Response Tips. So Scott, if you want to introduce yourself.
Yes, I'm Scott Hartley. I'm the CEO of ProEngine Inc. And one of the reasons why I wanted to have this topic in particular is I think there's a lot of misunderstandings about aerosols, and so if you also follow kind of where threats are going to, a lot of those are going to manifest themselves as aerosols. So there's more educational aspect of this, and hopefully it'll be beneficial to industry as a whole and first responders as a whole to just educate yourself about the nature of the aerosol threat and then how to deal with it.
Perfect. So just to remind everybody, we are recording this so that if there are things that you want to see or revisit, then you will be able to get that recording from ProEngine. The other thing to keep in mind is as we go along, there is a questions section or a chat area where you can ask questions or send chat information. And we'll be trying to watch that, but at the end of it, we'll get back and try to answer questions so we save time for that towards the end. So we hope to go right around an hour and talk about the different threats. So I'm going to turn off my camera so as not to scare you continuously throughout this. But other than that, we will go just to the slides and you'll hear our voices. So I'm going to turn my camera off and then we'll start in. Okay, so the topics that we're going to cover today are the evolution of the chemical warfare agent threats, the science behind aerosols and why they're important, some operational solutions to this, and applications on where they apply. Now, just like anything that you get from the ProEngine Academy, they don't just talk about their own equipment. They talk about the toolbox approach and how we can address these different aerosols from the overarching perspective of what can we all do to get where we need to go. So I'm going to start out just reminding folks where we are in the evolution of chemical warfare agents. And as you'll see on some of the slides, there's going to be these highlights of CBRN World Magazine, where you can find issues with more details on some of these threats, because we don't have time in a quick webinar to go into detail. But you can find those both on my website and on the CBRN World website. But what I really wanted to talk about was the evolution of how these different materials have come to fruition. So if we start on the top, that's going to be our anti-personnel materials. Those are materials that were designed to take somebody out of action, whether that taking them out of action was a temporary solution from a warfare perspective or permanent, meaning they died. Didn't really matter here, but these things were materials that were meant to take you out for a period of time. Now, most of those materials had higher vapor pressures, and that was because we wanted to get into that breathing zone. So in the early days, World War I, those materials were the choking agents and some of the blood agents, and they really were toxic industrial chemicals. So things like chlorine, things like hydrogen cyanide, materials that at that time trying to get heavy gases that would flow into a foxhole. Now, as you move forward into today's warfare, we don't actually fight in foxholes anymore. So the materials had to change to address the current warfare threat. But reality is, in World War II, the nerve agents came into play, the G series. And with those, they still had liquids with considerable vapor pressure. And then today, in terms of these types of materials, are the pharmaceutical-based agents. And of the 16 that we follow closely, 14 of them are aerosols or powders and are dispersed as an aerosol. So they're just suspended in air. Now, if you look to the bottom of the page, the same type of trend you'll see, but these things are all meant to be area denial materials. And in area denial, it's to give yourself an extra flank. It's to make sure that it's an area where people won't come through again. These often are also used as targeted assassination tools because they're very heavy, they stay where you put them, and they're very persistent. So with this in mind, we started out with the blister agents. So things like sulfur mustard, lewisite, those types of materials, very oily, thick materials that stuck to the area where you put them. Now, they did have gases that came off of them, but they were very heavy and stuck close to the ground. Fast forward to World War II in the V series nerve agents, VX, the one that we think about the most, but I could have VX sitting here on the table with me today. And unless I get up close and personal, touch it, get real close and try to breathe it in, it's not going to really affect me. However, if I were to put it in a space and somebody were to walk through it and things, then it becomes an issue. The same type of thing is what we see with the fourth generation agents, or the FGAs, or the Novichucks, whatever you want to call them. They tend to be liquids or solids, and they have very little vapor pressure. And again, they must be dispersed as an aerosol in order to get them to spread out. The issue here, again, with all of these materials on the bottom is while they're area denial materials, they're also targeted assassination tools. But as we came out to the modern day, almost all materials went from gas to a liquid with considerable vapor pressure to less and less vapor pressure to now where we're at the solids. And that's where it's really changing the game of how we have to work with these materials. So just to kind of to show you the same thing, as we went from things like phosgene to sarin to VX to the A series, you can see how the vapor pressure continuously goes lower and lower and lower. This makes it difficult for detection because we don't have a lot of material coming up to meet the detector. So we've got to figure out the ways that we can get the detector to meet the chemical and make sure that we're sampling in the right areas. But at the same time that that vapor pressure was coming down, you can see parallel on the right-hand side where the toxicity was going up, ever increasing. So now these materials are becoming more and more persistent while they're also becoming more toxic. Now, as we look at the threat, I know a lot of you have seen my threat briefs over the years, but this is where we are currently on the terrorism threat. And so when we start looking at the terrorism threat through the voice of terrorism chatter on different social media sites and different platforms, the chemicals here in red are the ones that we worry about the most. These are the ones that from a US-based perspective, I know many of you are not in the US that are online today, so that changes a little bit. In a US-based perspective, are things that we expect to see in the near term are toxic industrial chemicals, pharmaceutical-based agents, toxins, and then different homemade explosives and incendiary devices. The things that we expect to be on our horizon, but hopefully not in the very near term, are those traditional chemical warfare agents and fourth generation agents, as well as radiological. Now, unfortunately for many of you in the areas that you're in and operating in, you couldn't rule out your traditional chemical warfare agents or your fourth generation agents as things that are longer term. That's unfortunate, mainly in the Europe and some of the Northern Africa, Middle East regions, that those become a much higher threat based upon proximity to state actors that have easy access. In terms of the US, the traditional chemical warfare agent that we're watching for continuously at all times is sulfur mustard, mainly because of its ease of making it on the fly with traditional materials. So you can make a good mustard pretty quickly using things off the shelf. Whereas sarin and VX are much more prevalent threats to think about in the other parts of the world. Now, when we look at those are the things that people are talking about, chatting about, and the materials that they're talking about making and the methods that they're talking about using are realistic and would provide a, but I want a little bit different. And I hadn't thought about it from this perspective until Scott had come to me with some of these thoughts. And reality is, in the toxic industrial chemicals, most of the ones that we deal with are either gases or vapors. So those binary devices, the irritants, those generally, what we deal with have been gases or vapors. But as we get out to the pesticides and some of the other newer irritants, they tend to be aerosols as well. If we get down to those ones in orange, they tend to be a mixture of vapor and aerosols. Now, when we talk about mustard and VX, there's very little vapor there because their vapor pressure is so low. So they generally get dispersed, and then you start to see that. Whereas sarin going to be more of a vapor threat. But when you get down to all these ones in the red on the right-hand side, those ones are all aerosol-based threats. And most of the detectors that we deal with today, as well as some of the protection that we deal with, does not do well with aerosols. And then, of course, the ones down the bottom, the rad nuke and the explosives, are generally going to be solids or liquid-based threats. So allows us a little bit more flexibility with how to deal with them because they're not coming to meet us, whereas gases, vapors, and aerosols are coming to meet us. Now, I wanted to talk a little bit about what aerosols are to make sure that we're all on the same page. So aerosols behave just like they're a gas or a vapor, but in reality, they're a very fine liquid or solid particle that's suspended in a gas. Okay, in most of the cases that we're dealing with, that gas is air. But it could be just like you're thinking about with an aerosol spray can, where you have a propellant or other gases in there to help the aerosol flow. What's interesting about aerosols is while they behave like a vapor or a gas, they maintain the physical properties of their solid and liquid state. And that's what makes them so difficult to deal with. The aerosol formation takes advantage of their natural state, but you can also add materials that we call glidants or flow promoters. Those materials are the things that we generally would be able to see with our Raman and infrareds, but not necessarily be able to see as easily with our gas phase materials. But to get the Raman or infrared, we're going to have to collect a lot of material. On the aerosols, we generally look at them from their origin, their composition, what are they made of, the size, are they breathable, and then the density and concentration is, if we do breathe them, is it a toxic dose? So the operational implications that you see here mainly come into the health effects, because remember, now we're dealing with something that's behaving as a gas and moving as a gas. So we have a very high chance of impacting humans in getting into the respiratory tract. But these materials tend to stay in the air suspended much longer, and it depends upon the particle size. We went down this road quite a few times in the last few years about this 2-micron particle and how they like to stay lofted in the air for, if there's no interaction with it, it'll stay lofted for 12 hours or longer. But if there is interaction and airflow, it's going to be days before it comes out of the air. With these types of things, they're really increase your ability to use it in a large area. So when we talk about a mass decon event, we have to start out with a mass contamination first. And the easiest way to get a mass contamination is actually using aerosols. When we use gases, they tend to disperse too easily, whereas we take advantage of the aerosol properties, and that gives an area where they actually can spread for quite a ways. The problem that we have with aerosols, and we're going to talk about this a little bit more, is their ability to penetrate many of the protective clothing ensembles that we use today. And also their ability to defeat the detectors. So if you look at all of your detectors in your inventory and focus in on those trace detectors, just remember that any of your trace detectors that have filters on the end of them are going to negate their ability to detect an aerosol. So aerosols tend to vary in consistency. And so we're going to have to do a lot of continuous sampling to ensure that we're capturing the aerosols where they are. So the first thing I wanted to talk about was the particle size. And there's a reason that we have to capture certain particle sizes. And I divided them out here into the different phases of what we're doing in that early part of the response, where we're really focusing on what's coming out to get us. And in that case, we have the detect to warn, which is really where we're focusing on there is the civilian population that has no protective equipment on. So no respiratory protection, no protective clothing. What level do we need to be able to tell them there's a threat? And then, of course, for us, for the responders, the detect to protect relatives, where it's the respiratory and dermal protection areas. So for respiratory, we're focusing on things that can make their way through really filtering face piece respirators, because that's our lowest level of respiratory protection. As well as for dermal, we're talking about materials that can not permeate with a gas, but penetrate the materials, interfaces, seams, and closures. Now, based upon all the studies that have been done, the particle size we're really focusing on is between 0.3 and 10 microns. So really small, but focusing in on that area will allow us to capture materials that tend to get deep into the lungs and will challenge our respiratory and our dermal protection. So how do we know this? In the detect to warn posture, there's been a ton of studies about where particles reside and where they'll land in the lungs. And so when we think about those particles that are greater than 10 microns, they actually end up in the upper region. And that's where they get there from impaction. We may actually swallow those more so than get them into the deep lung tissue area. So those ones between 2 and 10 microns tend to get right down into the area where we're seeing it in the bronchi and the bronchioles. As we get down to that 0.5 to 2 microns, they get down to the alveoli, which means they have a direct pathway quickly into the bloodstream. Anything that's below a half a micron generally gets expelled when you exhale. So they come in and they come back out. So those very small particles tend to not be able to get lower into the airways unless they jump on and ride on another particle. So with that said, most of these particles that we're dealing with in detect to warn are going to be particles that deposit into the lungs and then diffuse into the bloodstream. Really not something that we're worrying about as much on a skin level, but that's because the skin provides such a great barrier material. In terms of respiratory, hopefully everybody has looked at this one before, but this is really about figuring out what size particle will penetrate our respiratory protection. Now, most of us thankfully have CBAs or self-contained breathing apparatus to our ease of access, which means that we can avoid any of these materials as long as we have a well-fitted face piece. But our lowest common denominator in respiratory protection is generally going to be our filtering face piece respirator. And filtering face piece respirators have multiple ways in which the particles are captured. With that said, we have to start thinking about which particle is going to make it through the easiest. And reality is that's the 0.3 micron particle. So when you see all of the different test data and the test systems where we use a 0.3 micron particle, that's because of all the particles in looking at the 5 ways in which a respirator works, that particle can get through the easiest. So just looking at gravity, inertial, interception, diffusion, and electrostatic attraction, we end up saying that that 0.3 micron particle will get through before anything else will. So from a respiratory perspective, that's where we target. Now I'm going to show you a video here, and it's going to take a couple minutes, but I wanted to show you how we test this in a PPE, chemical protective clothing realm. Now this video is from Resonate Learning, and we did a joint project to develop kind of a training program to let people see how we have to test PPE. And so I'm going to let this one actually speak for itself. But this is the particle inward leakage test.
Is another means by which the integrity of the full ensemble can be evaluated. In this case, fluorescently tagged 2 micron sized particles are used as the test challenge. These particles are intended to represent exposures of operators to hazardous dusts, aerosols, and radiological contaminated particles. The test involves a human subject putting on a solid black hooded garment. This garment serves as an indicator for particles that pass through the ensemble. The subject is first photographed under ultraviolet light to ensure there is no particle contamination present. The test subject then puts on the test garment in accordance with the manufacturer's instructions using an appropriate respirator. The seal of the respirator on the test subject's face is fit tested to ensure that it will not leak during the particle exposure testing. After checking the overall configuration of the ensemble on the test subject enters a chamber that has large fans circulating the fluorescent particles at a speed of approximately 10 miles per hour. test subject performs a series of exercises on an elevated platform before the blowing particles. These exercises include duck squats, body bends, overhead arm reaches, torso twists, cross-body reaches, and walking in place. During the testing, the subject changes his orientation with respect to the wind for evaluating all portions of the ensemble. At the conclusion of the 30-minute test, the subject exits the chamber and goes into a doffing area where test operators carefully remove the test clothing, taking care to prevent any transfer of the fluorescent dust to the black garment. In the dark room, the test subject is photographed under ultraviolet light. A portable ultraviolet light is also used to provide a close-up examination of the black garment to determine if any particles penetrated through the test ensemble. In this test ensemble, which represents a non-certified product, particle penetration is clearly observed on the wearer's neck and upper front torso due to a poor respirator interface and lack of storm flap over the front zipper. Ensembles that are certified using this test will provide complete protection of the operator from any particulate or aerosol exposure.
And I show you that one just because it does provide us a little bit of information about how these particles work. Now, with that said, that garment was intentionally shown because if we show you one that's going to pass, then you see no particles, so it's not very exciting to see. But in terms of our gear that we wear in the US, things that meet the NFPA 1994 or the NFPA 1991 standards, those things are all particle type. So you can see this material on the left-hand picture is a particle type ensemble. That ensemble actually has no chemical protective material on it, but it's still particle type. Whereas the one on the right, we generally tend to wear from a military context, and they're carbon impregnated, and they have some chemical protection, but the problem is aerosols tend to go right through them. So when we started looking at those types of materials, that 0.5 micron particle size is what goes fastest through all of these suits. And so when we start looking at some of the threat materials and knowing that a lot of these are aerosols, those 0.5 micron ones go right through and don't get stopped by the carbon and go right in. So that highest rate, about 75% of those particles will end up making their way to the skin level. With that said, the skin's a fantastic barrier material, but it does allow that threat to become a secondary contamination source because now it's made it through the gear onto the skin, and we need to make sure that we get it back off of the skin before somebody ends up re-aerosolizing it, getting it on their hands and ingesting it, any of those types of things. So Scott, over to you.
So I'm going to talk a little bit, excuse me, about flame photometric detection, which is one of the tools that you can utilize to help detect these aerosol threats with it. So this is a common instrument that you find in laboratories. So if you go to pretty much any chemistry lab or a lot of testing facilities, you'll find these equipment present there. Where we're different a little bit is the fact that we have a handheld that's portable versus a lot of these machines are very large and can fit on a full desk as a normal operating size of it. But what it involves is a physical phenomenon where if you apply energy to incoming materials, you can excite those materials, and then when they relax, they produce visible light, which we can then capture, and we look for the specific fingerprint of the materials that we're looking for. So I'll explain a little bit on the materials specific materials we're looking for in relation to some of your CVA chemical warfare threats with it. But you can just kind of see here, intrinsically looking at calcium, copper, and potassium, they each have a unique response that our eyes can differentiate. And what we're actually using are sensors that are a little bit even more sensitive than our eyes in order to depict and find those fingerprints of associated items. Next slide, please. So what we're going to show here is a video of the actual device being utilized, and we'll show how we're able to, and reasons why we're able to detect aerosol threats going through it. So what you're seeing here is the actual, in this case, the flame, which is what we're using to excite the incoming materials. And what you have up front of the detector is what we call a pre-burner area. So what it does is it helps, if you're operating in a flammable environment, it helps keep the materials, if they're flammable, from propagating outside of the device. So it acts similar to kind of how a silencer on a weapon does. But what you see here is the incoming airstream from it. So we have no filters between where you're bringing the air in into where you're pulling it out. And so therefore, none of the aerosol materials will be filtered out. So they come, everything that is in the airstream, we're basically bringing through there. So we're applying it to the energy state. And then what we're doing is you're seeing the response of those different materials there. How we actually collect the information is we have an optical lens and then a CMOS sensor. So what a CMOS sensor does is allows it to capture the light, and it puts it into something that a processor can analyze and look for the specific fingerprints of each of those materials. An additional advantage of the system is that we are able to see multiple materials simultaneously. So again, each material has that unique fingerprint, and we're looking for that fingerprint. And so we're able to identify it. And the second feature of the system is that there's a direct correlation between the amount of energy present and the amount of energy that's produced. So as there's more energy in the airstream, or the more atoms in the airstream, there'll be more physical light that's produced and more energy that we collect, and therefore it's a direct correlation between those. So it's both a quantitative and qualitative means of being able to identify some of these key materials. Next slide, please. So what we're going to show you here is the ability of the device to detect multiple CWAs. So in this case, we're looking at sarin, mustard, and VX. Now, a couple things relating to if you go back to the original slides that Christina had, is there's definitely a difference in vapor pressure differences between each of these materials. So the amount of vapor pressure directly correlates to the amount of atoms that are released, as well as the concentration of those materials that are released with it. So you're seeing the response time as a function of the vapor pressure, as should be. So as that has a higher vapor pressure, there's more atoms released quicker. They go through the detector faster, and we're able to see them. So the same thing would correlate to the amount of materials. If you have more materials present, there'd be more atoms present associated with them. Now, there's a response specific for each of these materials based upon the fact of what the channel of they're doing. So in the case of VX and phosphorus, each of the channels have a different sensitivity. So in the case of sulfur versus phosphorus, there's about a 50 times difference in the sensitivity level. And so what that explains in the case of VX, which has both phosphorus and sulfur compounds associated with it, if you notice that we didn't trigger that, and the reason behind that is the fact that there's just not enough materials present for that to reach the trigger point of the device with the concentration that we're dealing with. So if you have a higher concentration or you have a higher temperature of materials, then it can release that point. And then the next video will kind of demonstrate that in more detail for you. So in the case of this, what we have is a sampling system that can be additionally applied for these materials. So if you're dealing with a non-aerosolized powder, this is what's called the S4PE. We also have what's called the S4PF, which goes up to a higher temperature. So you take a sample of that, introduce that into the device, and you're able to release more atoms associated with that. So what you're seeing here is truly VX. By introducing more of the material, you're getting an impact on, you're seeing both the phosphorus and sulfur compounds. So in other words, you're seeing both a higher response on both. And just the fact that because of that 50 times difference between the phosphorus and the sulfur, you're reaching that higher concentration necessary to trigger both channels on there. And you still will see that there is a higher response on that phosphorus channel than there will be on the sulfur, which just correlates to the sensitivity of the device with that. But it's showing you another indicative means of helping to identify those materials by the triggering on both of those systems. Now, again, if you're talking sarin, I mean, you're at a much higher vapor pressure, but in the case of VX, because it's at a very low vapor pressure. If you're really wanting to turn that into an offensive weapon by aerosolizing those materials, you can basically you weaponize it. So you're bringing it from something that's not going to come out to bite you to can come out to bite you. So if you have VX that's just sitting there on the floor, it's not going to off-gas very much. It will off-gas enough that we're able to see it, but it won't off-gas to a point where it becomes more it's primarily just a percutaneous threat at that point, unless I played some sort of Jarwin games and want to go down and sniff it and bring that into my respiratory system. Now, if I weaponize that and aerosolize that, then that becomes, you're now releasing it into the atmosphere and bringing something that isn't a respiratory threat into a much larger respiratory threat, and that can take you down, especially if you aren't properly protected as far as a respirator to eliminate that threat from coming into you. Next slide, please. So what we're going to talk about next are your pharmaceutical-based agents. So what is a pharmaceutical-based agent? It's simply a subset of something that has medical purposes that can be turned into an offensive weapon with that. So if you're at a hospital, for example, they always ask your weight when you're giving, before they give you the amount of materials. So there's directly correlation between the amount of medicine that you're provided and your weight, because if you apply too much for your weight, then that can have a negative effect. And these are the same sets of concerns with your PBAs from the standpoint of they have legitimate medical purposes, but these materials are readily available. So they're present in hospitals and pharmacies and everything like that. In many cases, these materials can even be applied already in an aerosol, already solubilized in materials. And so therefore, all you need to do is find out a way of aerosolizing them. So they figured out in many cases they're already dissolvable into materials. And so all you need is a means of aerosolizing those materials, and you now have a fairly effective chemical warfare agent with that. Now there's different classes of materials. I mean, the opioids are kind of the most well-known one with it. So everything from your basic opium all the way up to your completely synthetic materials, which are your fentanyls and your carfentanyls, but there's lots of different classes of materials of those, but then there are a number of different other aspects or classes of materials with this, and there's really hundreds of materials that can result from these. So from a detection standpoint, that becomes much more of a challenge for us from the standpoint of just the pure number of materials and just their availability, right? So if it's something that's not readily available or super hard to synthesize, those become less of a threat. But if they're readily available or they can be acquired fairly easily, then they become more of a threat, right? Because you basically don't have to know the chemistry, you just have to have the access to it, and then it's just a matter of bringing enough down into the human body to have that effect, bringing enough of that material to target in order to be able to do that. Next slide, please. And so these are just some examples of well-known materials that or be PBAs materials with these, and these aren't all fentanyls, which are your basically painkillers with it, but there are a number of classes of materials with these that can be either they can either be incapacitating agents, they can be used for anesthesia, they could be paralysis agents. So there's a whole bunch of different of these classes of materials associated with them, and majority of these, or pretty much all of them, are in some sort of suspension or in a powder form that would need to be aerosolized in order to really bring that to target with it. So a weaponized version of it would be something that is usually dissolved and then aerosolized with certain effects to keep it aerosolized or in the air longer. It could also just be that powder is presented into the air and allowed to off gas. Now that's a less efficient way of doing it, but it still is a threat. And we see that sometimes with law enforcement when there's a raid or something like that, they flush it down, try to flush some materials down in a toilet, for example, and then you get the aerosolization effect associated with that, or just that being, moved into the air. That's not a super efficient way of doing it, but it is an efficient way and sufficient enough to get into our respiratory systems where it can really have more of an effect with these materials. Next slide, please. So just from a standpoint of powders in close contact. So what you will see a lot of times with these is they will tend to agglomerate, or you'll have van der Waals forces that'll kind of create an electrostatic effect of those. So they'll tend to agglomerate together with each other due to their charge. So a lot of times, I mean, if you've ever dealt with dust or powders, a lot of times they do have threats because of this electrostatic charge associated with them. It can actually turn some of these powders into potential explosive effects if they're at a high enough aspect of it. But these aerosolized things also contribute to their ability to get into the air. So if you go back to the original slides, one of the things we're talking about is the particle size of those materials is definitely an impactor as far as how long these materials can maintain into the air. So as a general rule, what you'd probably expect is if they're smaller, the particle size, the more ability that they have to stay airborne for longer, right? Just intrinsically, you know, gravity effects on things with it. So the heavier or larger particles will tend to come out of the air a little bit easier than the smaller ones associated with them, with their present. But why this is important to consider is if you do have, or in a response, for example, with the fentanyl, which is relatively common material, as you know, or carfentanil, which is even more potent associated with those, is if those have been aerosolized, it's going to take a amount of time in order for that to come out of the air. So if you're trying to do decon for these materials, which a lot of times is necessary, you have to understand that you have to let those come out of suspension, or else they could still be in the air. So just be cognizant of that as a potential threat to the first responders that are there in order to do that. And so and also additional component to that is the amount of turbulence in the air will also contribute to it, because it can help re-aerosolize those or get those back up into the air. So if it's in a closed room and there's no airflow in it, that'll come out of suspension a lot easier than if it's in something where the doors are open, or you have some sort of ventilation system that's going inside, or if you're outside, you're kind of at the whim of whatever's occurring as far as the weather that day. Next slide. So what we're going to show you here is a quick video of PBAs. And so this is a solution of fentanyl in methanol, and it's at a fairly low concentration as far as 1 milligram per milliliter. So there's nothing being done to this to purposefully aerosolize it or to make an aerosol solution. But you can kind of see just simply the dropping of that material on there, and through van der Waals forces, there's a fairly high concentration of this. So the concentration level for this, so you see we can kind of get up to about 4 bars on the hydrogen-nitrogen channel, which is where most of these opioid materials, pretty much most of your PBAs will show themselves out, because they all have hydrogen-nitrogen bonds in them. They're just fairly high concentrations. You're talking into the hundreds of parts per million concentration that you can just see from that standpoint. This is another example of what can occur when you add heat to it. So we do have what's called the S4PF and S4PE, which are sampling systems. The S4PF was actually, the F stands for fentanyl. So it goes up to around 520 degrees Fahrenheit versus around 380 degrees Fahrenheit. So if you're dealing with pure fentanyl materials, so either fentanyl or carfentanil, and it's not cut with any other materials, those materials in the pure form are at a much higher melting temperature. And so that's the reason why we went from the S4PE, which is around 380, up to the 520, which is the S4PF. What that does is it allows those pure materials to be aerosolized sufficient enough for you to detect and determine classes of materials that are present. Now, if they are present in an aerosol, in many cases you should be able to see those. But if they're sitting there in a powder form and you're, non-aerosolized powder form, it allows you to introduce those into the detector, and they'll hit on the hydrogen and nitrogen channel to indicate that those are, you have some sort of PBA present in the powder that you're dealing with. Next slide, please. And you taking over?
Okay, I'm going to start in a little bit about the 4th generation agents. And so I think everybody is very, but when we talk about the 4th generation agents in the US, at least, we're talking about the Novichoks. So those materials that came out of the Russian regime, starting back in the 1970s and 80s, where they were trying to find a replacement for VX, because the Russian VX did not have a significant shelf life. And so if we just start looking at the ways that it's been used over the years, most of the time it has been used as a targeted assassination tool as a dermal exposure event. And frankly, that's great because that keeps it in a space where it doesn't come out to meet others. But what we do know is that when it is aerosolized, as seen in 1987 with Andrei Zhelezhnikov, as well as with Dawn Sturgis in 2018, things do not go well. So if we just go through these real quickly, so Andrei Zhelezhnikov was working in the laboratory and the hood was not working properly, and so he realized that he was exposed. Luckily, he was right there in the lab, and the person there with him was able to give him some antidote pretty quickly. At that point in time, it was the traditional atropine 2-PAM type of antidote. Did not save him in terms of longevity, but it did keep him alive, and where he lived another 6 years before he passed away. Unfortunately, with most of these types of materials, the damage that's done at the original intent is damage that stays with you forever. So in 1995, Ivan Kavalidi was targeted, and in this case, they actually went through his ear. And so they used the material inside the phone. So they took the speaker cover off of the phone. So took that off, put the material underneath the phone speaker, and then put that back, the cover back on, and then it seeped its way through to his ear. The ear is one of the most permeable areas on the human body, which is why they target it that way. The Gabrevs and the Skripals were both targeted using their hands. So the Gabrevs were arms dealers, and it was via the door handles on their cars, whereas the Skripals, it was the door to their house. Dawn Sturgis and Charlie Rowley were unintentional targets, and it was just the throwing away of the material in the wrong bin, which ended up causing their exposures. And then, of course, Alexei Navalny, who was targeted for assassination many times. But in this case, they actually went through the scrotum, which means it'll go through much faster because it's the thinnest area of skin on the human body. So much more permeable than even the ears that the Kavalidi target was for. Now, when we look at that, the reason I bring those up is just to show you the time to symptomology. So Zhelezhnikov was actually immediate. He knew that he was exposed. He actually got the person there in the lab to provide him with antidote and was able to stay viable. Dawn Sturgis, on the other hand, if you come down to the modern day, she actually was the one who sprayed the device, thinking it was perfume. And she inhaled it. While she did live for a length of time, she ended up passing away from that. But her response was almost immediate. By the time Charlie Rowley came out of the bathroom, she was already exhibiting the symptoms. So he went in to wash his hands, came out. And so we know seconds to minutes was how long it took for her to have those symptoms. What's really interesting with these materials is that the way that you get exposed dictates the symptoms that you get. So in terms of Dawn Sturgis, her symptomology was an inhalation symptomology, which means it gets into the bloodstream and goes systemic pretty quickly. Whereas some of the others were all through the skin. And in that case, it takes much longer before you start to see symptoms, number one, because the skin, as we've said before, is a very good barrier material. But it takes hours before you get any symptoms. And those symptoms tend to be focused in on the perspiration, hypersalivation, more so than those pinpoint pupils. Now, with that said, if you come down to Navalny, who had the dermal exposure through the scrotum, he actually exhibited that gastrointestinal pain. And the reason I bring these up is we teach people all the time about sludgem, salivation, lacrimation, urination, defecation, gastrointestinal distress, emesis or vomiting, and constricted pupils, meiosis. But what we fail to tell people is that those symptomologies of a nerve agent exposure actually come out once it's actually in the bloodstream. So a lot of these, depending upon the way in which you're exposed, don't show up. So we've been training people for years of these different things to look for in terms of a chemical exposure. Another good example is hydrogen cyanide. We talk about the reddening of the skin and how everybody's going to have that beet red skin from a hydrogen cyanide exposure, yet we only see that in cadavers. When we have somebody who's salvageable, we don't see the reddening of the skin. And so that's where detection early is going to be critical. Because if we wait for that onset of symptoms as our early detection, we're actually probably going to lose the patients. So I want to show you this just because based upon the vapor pressure that we see of the FGAs or the Novichoks, just remember that this is even 10 times less than what we had available for VX. So this video we're going to just run and show you, and this is in the laboratory obviously, and you can see the sand bath right there to keep the temperature constant at 25 degrees so we don't heat up any of those A-series agents. So this one's A230, and you can see that in about 8 seconds you started to see a response. This is pretty impressive because we generally have to worry about these materials being such a low vapor pressure that they're not coming out to meet us. And so they generally stay in an area for a long period of time based upon their persistence. Now, as we get to A234, higher vapor pressure doesn't show up as fast. So you're starting to see these things that take a little bit longer. If you went ahead and did it with the AP4, the S4PF or the S4PE, you'll end up getting that temperature up high and quick. So it does allow you with the ability to see the systems in gas phase, which is really incredible, but also allows you to look at that solid and liquid quickly if you need to. Now, the reason I wanted to bring all these things up was to show you this. As we start looking at our detection postures, our detect to warn, our detect to protect, whether it's respiratory or dermal, and the detect to decontaminate, all of these things are critical events along the way to a successful risk-based response to an aerosol-based threat. In order to do this, we need to be able to do that continuous monitoring. So our early stage detection, the only detector we have available that can do this is the AP4C, and that's why we team up to show you this. If we want to get into the detection side, then we'll have to do batch sampling, and we can do the 1.5 minutes or so, and the MX908 is a fantastic tool to get you there. Now remember, on the MX908, it's capturing particles that are 2.5 microns in larger. However, we're very hopeful that some of those small particles will agglomerate and will allow us to detect them for those respiratory and dermal threats. But again, batch sampling, 1.5 minutes. If you're using the aerosol module, it will allow you to collect and then every minute or so thermally desorb those samples off. Now there are other tools that you can use as well. You can use these other tools post-event. And so GCMS, you can do a white sample where you extract the material off and then run it in your GCMS. If you're using one like the G510, you can get a 6-minute runtime and still get your sample. For Raman or FTIR, as long as you get enough residue on the surfaces or gather up some of that material, you can then extract it and run it on the Raman or FTIR. Or if you get enough post-material residue, you can do direct sampling. And then, of course, for a couple of the different threats, we do have colorimetric tools as well. Again, we're going to need to have quite a bit of material there, but that would allow us to come up with a capability set. Now, in terms of chemical detection, generally I use the Raman or FTIR or even the GCMS as a way to detect what glidants or different materials were added to make the threat stay longer in the air. So things, won't get into the exact ones, but there's quite a few different glidants that we can use or that are talked about that would show up on your Raman and FTIR. So definitely a piece of kit that you want to have with you, but not going to help you in that first immediate response to telling where it is, when it is, and then using your 908 to identify uniquely. So just remember, you've got to balance that detection capability with response times, the size, weight, and cost of the instrument. In reality is we need a continuous monitoring because of the way that aerosols don't stay all in the same space. Scott, I'm going to turn it back over to you.
Yeah, and just one additional comment relative to the particle size and the detection capability. When it comes to aerosol threats, you will see some, there's two things. One is that it's not going to be a uniform concentration of materials associated with those, especially in comparison to a vapor threat, where those materials are going to be much more uniform in nature associated with those. So you're going to see concentration gradients based upon some of that's correlating to agglomeration of materials, but then just also due to the somewhat random nature of those, because those aren't going to be uniformly dispersed in many cases, unless it's a state actor that has very good dispersion capabilities with there. And there's actually a fair amount of science associated with that. But you will see a response as a function of particle size to those materials. Now, we do have some ongoing efforts on the AP4C Plus, which is the newer version of the AP4C, which is in testing at Edgewood. And one of the things that they are in process of going to start to do is some PBA testing at different particle sizes. So we're definitely interested in just learning a little bit more about that, just from the standpoint of when you get down to particle size capabilities, there's only a few places that can really test it to the weaponized variants of those. And so we're definitely looking forward to getting some more data and more knowledge about the performance of those different particle size materials. Next slide, please. I'm going to talk a little bit more, just switching topics slightly on it, but it does apply to it. An additional component of aerosol threats, going back to what Christina was talking about earlier, are biological materials. And these will primarily present themselves as biological materials. And flame spectroscopy can be an additional tool that you can use in that tool box in order to help detect these materials. And I'll talk a little bit more about how it is what we're doing. We do have planned later this year to have a full webinar specifically talking about this topic. So we hope that will definitely get some interest on there. But if you just kind of, from the standpoint of, there have been some a lot of work being done, especially during the COVID or post-COVID time periods, on identification of materials, and there are different with this. One of the challenges of those technologies, and kind of one of the challenges of, for example, the BioWatch program, is just knowing when to take a sample associated with that. And that's an area actually where flame spectroscopy can help out associated with that. It's very good for sitting there 24 hours a day, 7 days a week, or during a certain time period where you're looking for, by establishing a baseline of the biological performance level that's present in the environment, and then you're looking for any sort of changes associated with that. And so how do we do that? We're looking for we collect information on additional channels of information. So we're looking for sodium, potassium, and calcium in the airstream. And if you have those materials, those are indicative of RNA that's present in these materials. So specific ratios associated with them are present in different biological materials. Now, that is different than toxins. So as we also talked about those, a lot of times toxins are considered to be biological materials because they're biologically derived either through plants or animals associated with those. And so they tend to be considered to be biological threats. A high percentage of those will present themselves on chemicals. They behave similar to chemical warfare agents as far as their physiological response that's resulted in the humans, and they will be picked on the hydrogen-nitrogen channel, a high majority of all of those materials, all those toxins, they're associated with it. When we're talking with an actual biological, so something that will make you sick and have a immune response associated with it, the AP4C technology can be utilized for those materials. And the next slide, we'll talk a little bit more about those. And there'll be a little bit of, you'll have to press the space bar a little bit for me to do that. So you press this, basically what we have here is we start the detector and we can establish a baseline of the background level. So one of the challenges with biological materials in particular is that the amount of biological activity is not uniform. So it will vary by time of year, location, and other things like that. So the amount of biologicals that are just baseline materials that are presently in the airstream will vary based upon, if you're in Alaska in the middle of winter, it's going to be drastically different than a tropical rainforest, say in Florida, just because of the temperature and the ability to grow and support these materials. So you first have to establish a baseline performance level. So we do that by running for a number of minutes, establishing a physical baseline. And then you're looking for any sort of abnormal effects that are resulting from that response. And then that's indicative of some sort of purposeful release. So one of the ways that these materials will be done is they will be released as aerosols, and they will you don't have an infinite supply of these materials, and so there is a baseline, and you're changing the performance of that baseline, and then you'll have a response that goes down. In many cases, it won't be for hours, unless you're dealing with some sort of state actor, most likely. But if there's some sort of release, there'll be a change in the biological baseline of that, which then indicates a trigger of that, and then that will go down after the materials go away, and because it's kind of a batch release. So once that batch stops, you'll start down, and then the alarm will go off. But what that can do is then sense when I need to take a sample of these materials and then run through of that, versus just randomly taking a sample at certain periodic elements, not knowing when exactly that biological event's going to do it. So you may hit it, you may not. But even if you hit it, it doesn't necessarily tell you. So this is a way of correlating associated with that. So we can use that to trigger other materials. We can also do that to trigger sampling solutions as well. So there's both liquid and dry sampling solutions, which you then can run and give to a laboratory as well with that. So we've experienced with both of those being able to do that. So it's part of a holistic biological response with aerosolized materials, which again, that's what this threat profile will present itself as, is primarily aerosols. So it's an additional aspect or additional capability of the technology that exists with them. Next slide, please. So what we do differently with our biological solutions, if you notice, we have the AP4CF is our 24/7 one. We have a MAB, which is also can run for extended period of times, and the BB, which is a vehicle-based solution with those. So we add the biological capability to that. So we differentiate between our chemical to our biological ones by adding the B. And in many cases, especially in the case of the FB and the VB, these are both biological and chemical. So we're doing all the chemical channels, and then we add the additional sodium, potassium, calcium, and the additional processing capability associated with them and the algorithms on them, which requires a little bit more processing capability, and that's what differentiates those the FB from the B. So they will look similar as far as the casing as they come in, but they have different internal componentry in order to create add the additional biological capability to there. But one of the unique aspects of flame spectroscopy or FPD technology is that you can do simultaneous chemical and biological detection, which is somewhat unique in comparison to other system materials associated with them. So you can use those to collect samples or to trigger an additional sample. For example, if you want to use PCR, you can use that to correlate, and you can tie those together as part of a system approach to biological detection. Next slide, please. So just to highlight additional webinars, as we talked about in December, we're planning to talk about biological and in much more detail from that kind of truncated response I just gave you there. But our upcoming ones in July, we're going to talk about battery response. As you know, that's an ongoing thing, especially with the propagation and the more use of batteries, and especially with certain battery chemistries, which have chances of going exothermic and then creating much more responses. So some of the gases coming from there can be very harmful. The AP4C can definitely be used as a tool to help quickly identify classes of materials. So that's what that one's going to talk about. And then talking about irritants, both commercial and homemade threats. So these will also be, again, an aerosol type threat. Most of these will propagate themselves as an aerosol threat, but the use of irritants is growing. especially on the homemade ones being used against law enforcement or for civil unrest associated with them. So we will talk in more detail about them and how the FPD can be another tool in your toolbox for responding to those. So that kind of concludes our presentation for today. We just a little over an hour, so we kind of hit exactly what we're doing. So hopefully, if you have any questions, definitely please ask those and we'll work to answer those for you.
So far, I'm not seeing any questions today in the chat.
Does that mean we did such a good job of explaining things? Or we confuse people who, depending on which way you want to look at it.
Oh, his hand is raised. Noel Fitzgerald. So Noel, can you type it into the chat so we can see it? I can see a hand raised, or type it into the questions. Yes, I can see you typing now. Did you have a specific question?
It's kind of like seeing someone respond to your text, but you don't, they haven't
Yeah.
come through, but you know that they're there.
Thought effect, yes.
You're like, yeah, if any of you have questions, feel free to ask through the chat component.
Chat or questions, yeah.
Yep.
So one of my big things is making sure that everybody, especially so for, I'm thinking mainly from the US perspective right this second, is we have a lot of turmoil going on right now around the country. And one of those things is with the increase of protests and the increase of anti-law enforcement types of protests as well. With that, a lot of the threats that people are talking about have been on that aerosol base, which is why we wanted to bring this to you so quickly. And so aerosols are becoming more and more of the problem. The problem that we're having is that we have very few ways to detect them. And so that's where we have to start thinking about what are we going to do to either capture more information or go from there. Can something like a TSI be put in line? Yes, so no, yes, talking about the particle sizing, when you get into the bio type of events, that is exactly how that is done. So in terms of the bio, the particle sizing is done to target in on which particle sizes you want to capture. In terms of the chem, it's the AP4C collects more of the small particles and it's very efficient at the smaller particles that are breathable. Whereas a lot of other systems don't do as well on those small breathable particles. The problem that we have there, and we don't as much care per se on the chem side because we have multiple different approaches there, whether it's going to be dermal, that type of thing. But on the bio side, definitely those TSI systems are used in parallel, and that's why we put on it was agnostic, but that's 100% how it's done. So generally, if we say that it's just doing particle size, that's a trigger, whereas particle size along with something like an FPD is a cue. And so from a bio perspective, that's the two terminologies that we're using. So yes, we definitely use those particle counters from TSI and others.
I would say the additional data that an FPD is going to give you in that case is the biological componentry of those. So just because they're within that the area of interest, the 0.5 to around 10 microns, doesn't necessarily tell you if they're biological materials or non-biological materials, versus we're able to delineate that by the presence of those materials, which are indicated from RNA.
Okay, then another one, ever tried an aerodynamic lens on the front of the AP4C as a pre-concentrator? No, because right now it's, frankly, sometimes it's too too sensitive. So the last thing we want to do on an AP4C right now is to make it more sensitive because it's already at that low end. So we're measuring, especially in phosphorus, where phosphorus, you need the low end for your FGAs or your VX type of materials. When it comes to a lot of the other threats, it's just too sensitive, meaning it's measuring well below permissible exposure limits. So something like phosphine, I can measure at levels that are so low that they aren't relevant. But I can still measure at the higher levels as well. So yeah, a pre-concentrator on an AP4C, we haven't had a need for. However, on some of the other detection tools that we're using, definitely trying to use a pre-concentrator. So that's going to be the approach for any of the other technologies that we're seeing, is they're going to have to get some type of pre-concentrator in line to be able to do the work. Trying to see if I can get these to pop up. Okay, so I think I've got those ones. With that, I guess we will end for today. Don't forget, as always, you can get copies of the video and materials that will come out in parallel from ProEngine, and they're all available at the ProEngine Academy website. Scott, do you have any final remarks?
I'm good.
Okay. Thank you, everybody, and have a great day. Stay safe.